Well, hello there. Today's lecture is all about L'Hopital's rule, which is a simple, very powerful way of computing limits that up to now we were unable to do. And these are generally limits in the form 0 over 0 or infinity over infinity. And let's make a statement of L'Hopital's rule, and then we'll do a lot of examples to help you understand how to work it. So here simply is what L'Hopital's rule says. Suppose we have two functions, f and g, and they are differentiable. And let's suppose that they're both 0 when x is a. Then, when we think about this limit, as x approaches a, of f of x over g of x, which will be an indeterminate form of 0 over 0, what L'Hopital's rule says is that that limit is exactly equal to the limit as x approaches a of the derivative of f over the derivative of g. Now notice this is not the derivative of that. This is much simpler. It's just a derivative of the top over the derivative of the bottom. That's L'Hopital's rule. Simple, powerful. So this really isn't a formal proof, but here's why this works. Let's let L be the tangent line to f, and M be the tangent line to G at A. So therefore L of x is equal to this, and M of x is equal to this. Now let's remember that f of A and G of A are 0, and so that if I look at the quotient of L of x over M of x, these are 0, f of A and G of A. The x minus a's cancel, and all I get is f prime of a over g prime of a. And that's basically the reason why L'Hopital's rule works. Okay, back to examples. So a couple of things in passing. We want to always make sure that the conditions of L'Hopital's rule are met, which means that we're of the form 0 over 0. So if you look at these two examples, these should look very familiar to you. Here's where we can show, using L'Hopital's rule, that the limit as x approaches 0 of sine of x over x is 1, and similarly why 1 minus cos of x over x is equal to 0. So those were very important limits that we used when we were trying to find the derivative of sine and cosine. So here is what we would call the extension of L'Hopital's rule. And in this case, what we're looking at is the limit as either x approaches a or infinity of f of x. And if that equals infinity, and the same thing happens with g of x, so in other words, we're getting infinity over infinity, which is another indeterminate rule, then the limit as x either approaches a or infinity of f of x over g of x is equal to the limit as x approaches a or infinity of the derivative of f over the derivative of g. So in other words, L'Hopital rule can be extended to the case where we have, let's write it down, where we have infinity over infinity. Okay? So now we can tie up a loose end that's been hanging around for a while. So let's suppose we're looking at the limit as x approaches infinity of e to the x over x to the k, where k can be any positive integer. So in other words, this is basically representing any possible polynomial. So in this case, imagine that we are going to apply L'Hopital's rule k times. If we do that, this becomes the limit as x approaches infinity of e to the x, because you can take the derivative of e to the x as many times as you want, and you're going to get e to the x. But try to understand that if you take the derivative of x to the k times, you're going to get k factorial. And so what we have is something of the form infinity over a number, even though that number is really big, and this is infinity. And so what this shows is that e to the x dominates, is bigger than any polynomial at infinity. And that is an idea I think that's come up a couple of times, and now this is why it works. Okay, so let's look at some other examples. Okay, so let's take a look at this. Here we have, as x goes to infinity, ln of x over 2 root x. So both the top and the bottom go to infinity. So we can use L'Hopital's rule, and we get 1 over x over 1 over square root of x. And now, just by simple algebra, that comes to equal 1 over the square root of x, and as x goes to infinity, it's 0. All right? So I can't overemphasize how helpful L'Hopital's rule is in getting a handle on some of these indeterminate type limits. Okay, so we'll look at 2 examples that use some interesting tricks. Now, when you look at this expression, by now you want to use L'Hopital's rule, but we're not in the form of a quotient. And so here's the trick that we use. And what we're going to do is we're going to let h equal 1 over x. So this becomes the limit as h approaches 0 of the sine of h over h. Well, we know, we've already shown, that equals, remember, 1. Okay, that's example 1. Here's the next example. Okay, so before we even start working on this limit, let's just think about what's happening here. We have a number which is a little bit more than 1 being raised to a huge power. Well, if you take something bigger than 1 and raise it to a big power, you would think that it goes to infinity. But as x goes to infinity, this is basically going to 0. And so you have a number which is just 1 being raised to a huge power. Well, that's just 1. So we have what I refer to as a dynamic tension. What's going to win? The fact that this is just a little bit more than 1, and this is huge, or the fact that this is going to 0, this whole thing is going to 1, and when you raise 1 to a big power, you get 1. So what wins, 1 or infinity or something in between? Well, we use the same trick, and we say, let's let h equal 1 over x. And so this becomes the limit as h goes to 0 of 1 plus h to the 1 over h. Now, it doesn't seem like that's helped us a lot, but watch what we can do now. So this trick is a little bit beyond the scope of this course. It's a fact that you'll learn when you take a course in college called real analysis. But what I can do is take this limit and essentially take the ln of both sides. And I guess what I need to do is say that let's assume that this limit is equal to some number L. And what we do now is we take the ln of both sides. And the big property is I can take the ln and bring it all the way in. And so this just becomes the limit as h goes to 0 of the ln of 1 plus h to the 1 over h, and that equals the ln of L. Okay? So now I can make use of the properties of logs, a rule that some of my students call the down in front rule, and we can write this ln as the ln of 1 plus h times 1 over h, or just over h. And remember, that has to equal the ln of L. And so now we can invoke L'Hopital's rule on this limit. And we can write this as the limit as h goes to 0 of the derivative of the top over the derivative of the bottom. And that equals ln of L. Well, that limit is just 1, so that means the ln of L is equal to 1, And so finally, what we get is that L is equal to e to the 1, which means then, we'll just write it out again, that the limit as x approaches infinity of 1 plus 1 over x to the x is equal to that very, very special number e. Ta-da! So that's enough examples, I think, to give you some idea of how L'Hopital's rule works. And that's it for today. See you later.